Good morning, everyone. How was our night? Huh? Okay. So, what did we do yesterday? We did PCS. And how? Okay, we did PCS, we did KZG. Okay, can somebody just give us like a brief overview? What was the thing you went on with yesterday? Like, what did you pick out of the 5 hours, the 5 hours class?
That you can carry out competition.
Right, okay, everybody's ready to talk. One by one.
Okay, so I learned about we have the PCS, which when you add it to it reduces the size of the
Of the- No, not the size of the computation. But I get you. He said the PCS, when we add it to the IOP, we get a succinct proof. Yeah. Yeah. Okay.
Yeah, I didn't that's good. Because of the elliptical properties, like you carry out computations with a value that you don't actually know.
Okay. So that's Yes, this is
Yeah,
something.
I learned like how elements have been added, or should I say values have been added in the elliptical, and how they mirror each other.
Okay. So that's basically homomorphism,
Yeah.
right? Working with encrypted values. Okay.
Okay, I learned about the trustless setup.
Not trustless, trusted.
See, okay, so I have a problem. I mean, I know obviously like the industry standard, and I'm talking about it in over. But the trusted setup, the idea is that you don't need to trust it, right? So why do they call it?
No, the setup is trusted because the people involved need to trust that they are going to discard. There is an atom of trust in generating the random value. So there is that atom of trust when generating the random value. Everybody involved somehow trusts.
Reality. Hope they're not recording me.
Well,
No.
I don't know how to
Okay,
So there's that atom of trust between the people involved in the trusted setup, right? So the idea is that you believe that another person is going to throw away the person's own randomness, and you're going to throw away your randomness.
So
So,
it's actually trusted.
so it's actually
It's
trusted,
trustless.
no, not trustless.
So in the system where we explain what I learned, so that's the
Okay. Yeah. What did you learn yesterday?
Yesterday.
Okay. No, so what was it?
Yes, that's Tao. There is one not to anything. Okay, so like let's be quick so that we jump into what we have today. We have half time today. Yes. For the implementation.
Implementation of what?
of GKR.
Okay.
So continue your GKR implementation.
Like the one we did before.
The one you're still
The
doing.
one we
The one
we
you did
did
that
last
is not working. The one you did that is not
Yeah,
working.
this last one that we not yesterday.
No.
You know the yesterday.
No, your normal GKR that you're working on. So let's be fast.
Yeah, I learned about
Okay.
KZG
KZG.
and visual property which are management, holding and evaluating. So
Hiding and binding, right?
So another thing I learned that I really like is the structure of the editing curve. So yesterday I was able to see the associativity property. And I was able to add, like for example, that R is equals to P plus Q,
Yeah.
which P is a coordinate in the
On the call.
and the Q is a coordinate. So if I say P is what x1, y1, Q is x2, y2, our R will be x3, y3. So I'll be able to draw the relationship, the addition relationship. That means for me to get x3, it will just be m squared minus x1 minus x2, which is m in the slope x1. So I can do that for my y3 also. So I check the associativity property and I check that we can actually make the abelian the elliptic curve abelian also because of the symmetric nature of the graph.
Yeah. Yeah, because like when you draw a line, right? It doesn't matter if you're going from A to B or B to A, it's still a straight line, right?
I have to ensure that the distance is always positive wherever the direction you are coming from.
Nice. Nice. Okay, so who else wants to go? Let's just be quick. Okay.
I think that we can always make a point. So from the KZG formula, we can always make a point, a root based on how the formula is structured. So given a point, even if that point is not a root, when you evaluate it and get the value, then the f of x minus that value will automatically make that point a root. Then, and once that point is a root, when you do x, you divide the whole polynomial by x minus the point where you evaluated that is going to give you
Quotient.
quotient polynomial and the remainder, which will always be zero if the prover is telling the truth and all.
Nice. Nice.
I
Okay.
learned that polynomial commitment, right? I learned what polynomial commitment actually means, which is that like you have some sort of values and then they all map to one particular thing which you are going to be using instead of all those other values, committed values. So moving on for future use, you're going to be using that one value. So I really want to do that. And also one thing that struck me was the bilinear theory, where like instead of just like the additive multiplication I got about where I'm raising g to a scalar. So now instead of just a scalar, we're combining 2 points. And he said that that's the only possible using bilinear. I don't understand it yet, but I was striking.
Okay. Nice. Who else wants to go?
Yeah.
So I have a question for you guys.
Okay. Sorry, question, right? Oh, wait, then.
Yeah, it's really interesting how the native curve is how powerful it actually is. In the sense that, just like you said, it does not carry out multiplication, but the way it duplicates itself, to be able to get, to be able to perform as though it's carrying out those multiplications and stuff. It's kind of like adds a kind of better layer of like security again, because it's not just saying okay, this value times this. It's getting the minimum value okay at any point that you are going, thereby adding a kind of, so it's not easy for you to just crack it at one point and just know that okay this is it and stuff like that. Like it has so many movements, and the way Tao is able to make us laugh and also able to like this, get us to where we actually started for. It actually, it's more like revealing without revealing and stuff like that. So like the whole concept is kind of like interesting about.
Okay, nice. Like everybody has said some good stuff, and it seems we are following. So today, yesterday we wanted to talk about the trustless setup, right? And then, like the things we wanted to talk about yesterday that we did not have time to talk about are the trustless setup, right? And also, we looked at how an honest prover generates a proof, right? We can remember, right? Yeah. So we also wanted to look at how a dishonest prover will generate a proof, or an invalid proof. And then we also wanted to look at how a prover that knows how can generate a valid proof for a wrong statement. So these were the three things we wanted to look at yesterday. So we'll be looking at them today. Right. Trustless setup. Dishonest prover, invalid proof, and prover with the knowledge of Tao. Generating a valid proof for an invalid claim. Okay, so let's start with the trustless setup, right? Okay, so first of all, let's recall our indices, right? So if we have G, which is a generator, to the power of A times G to the B, what is this equal to? G to the A plus B, right? If we have G to the A times B, what is this equal to? G to the AB, right? Okay. So with this knowledge, let's see how we can take advantage of this knowledge, right? So to generate our powers of Tao. We can remember how to evaluate a polynomial, right? When we have an array of coefficients. Can we remember? How is that?
How you generate what?
How we want to evaluate a polynomial, and we have an array of the coefficients of that polynomial.
You multiply by the powers of
They're like
You will separate
powers
it
of
first.
x,
Yes,
right?
we have an array with x0, x1.
So we have an array with, okay, let's say our polynomial f of x is a plus bx plus cx squared, right? So how are we going to do it? A, B, C.
Not product. X is by 0, x is by 0.
Right?
Yeah.
So when we do an element wise product, we are going to have ax to the 0, bx to the 1, and cx squared, right? And when we add all of them, we have a plus bx plus cx squared, right? Good. So now this is in a case where we are working with x in the clear, right? When I say in the clear, I'm saying like we are working with the value of x, right? But when we don't want when we don't want the party doing the computation to actually know x, what can we do? We can encrypt x, right? And how do we encrypt x? Using an elliptic curve.
Raise it to the power of the generator.
We raise it to the power of it. Sorry, we raise the generator to the power of x. Okay. But all of us understand. So in order to do that, x is a scalar, right?
Yeah.
X is a scalar, and the generator is a what?
Is the point.
The generator is a point, right? With xy coordinates, right? So if we encrypt x, what are we going to get?
Another point.
Are we going to get a scalar or a point? We are going to get a point, right? Okay, good. So
How do you
Hmm?
How do you get the point?
it's because G is a generator, right?
And why would you get the point when you encrypt x?
That's because when we raise the generator to the power of x, right, we are just adding the generator to itself x number of times. Adding 2 points to it. Okay, let's say we have g, right? Or let's say y equal to g to the x, right? And g here is a point which has x, y coordinates, right? Basically, if we want to think about it in terms of a graph, the generator point can be here with its x coordinates and its y coordinates, right? And if we want to add this point to itself, okay, let me just draw the elliptic curve so that right. So if we're talking about this point, it has its x coordinates and it has its y coordinates, right? And if we want to add a point to itself, we draw a what? A tangent, right? And where it's cut, we mirror it, right? If here is P, then here is 2P, right? 2P is also a point, right? Because it has its own x coordinates and its y coordinates. So if we continue adding P to itself, or if we continue adding, okay, let me call this G, so that this 2G. If we continue adding G to itself, we're just moving randomly around this elliptic curve, right? And any point we get is actually a point which comprises of x and y coordinates, right?
Sorry, from the beginning, I'm very so if you want to draw the 2G, for instance,
Yeah.
are you going to draw a tangent to 2G?
No, because we have 2G already and we want to add G, right? So we know our G is here, so we're going to draw the line from right and say this is where it cuts. Forgive my drawing, but you get the point. Yeah. So this will be our 3G. Right. So if we want to add G again from the generator, yeah. But there are efficient ways of doing this addition where when we get 2G, we can add 2G to itself to get 4G, right? But like that's like kind of like an optimization, and I don't know if it works for all codes, but that's like an optimization.
Is it visually possible? Is this something you can point out like using?
I can point out like this. I don't think so. I don't think so.
The rest mathematical.
Yeah. Okay, so this makes sense, right? Does this make sense? Okay. So now, if we want to encrypt these values, because we want to hide x, right? So we can encrypt it by doing g to the x to the 0, right? G to the x to the 1, g to the x to the 2, blah blah blah, right? And this array is going to be an array of points, right? Because each of these values here are points. They have x and y coordinates. Okay.
So, if you want to hide x, right, x will be known at first.
For now, x is known, but we are going to talk about how we can generate x without knowing x. That's the next thing we are going to move into, the trusted setup ceremony. So, this is what to ask the question now when we get there.
No, I think I'm just trying to figure out how, like, x is,
How x is not known.
yeah, so, like, trying to, like, picture it like, okay, the generator, yes, we know, and we know once you raise a generator to x and you get the point, you cannot reverse engineer it to get x out of it. But at the first instance, when you're raising the generator to x,
Yeah, you will know x.
you know x.
Yes.
So I'm trying to like, okay, like how? Because trying to like, let's say we are generating a random number and raising g to that random number, right?
Yeah.
I guess this is a point where we have different people that brings their x,
Yes.
right? That brings their x, so they all know their individual x's. But once they bring it together and generate that stuff, nobody knows. Everybody knows their own. You can just kill one person and so
Okay.
it's
Yeah.
forever.
Yeah, so that's why like trusted setup actually requires a lot of people, right? Because if we have a trusted setup where it's just one participant, then that person definitely knows X.
So the x is what each participant is bringing.
Yes. So everybody is contributing their own X. So make X random. Okay. So we are going to talk about that say now, right? But this makes sense, right? How all these things are points. Right? Okay. So we remember this law, right? G to the A or to the B is equal to G to the AB, right? So this G to the A is a point, right? And then we are multiplying it with B. which is just adding that point to itself b times. We start with the generator, we add it to itself 8 times, and then add that result to itself b times, right? And then we are going to get g to the ab, right? So that's basically what makes the trusted setup ceremony. That is what enables everybody to contribute to the trusted setup, right? So let's say we have, let's say at the beginning, right? At the beginning, somebody brings x, or let's say somebody brings a. That's the person that initializes the trusted setup. The person will bring the person's own a and encrypt it, g to the a, right? So the person is going to do g to the a to the 0, g to the a to the 1, g to the a to the 2. Does this make sense?
Is it one person that is bringing all the keys?
Yeah, so the person just brings one a and then like raise that a to the power, right? And that's how, okay, just imagine that the person brings a0, a1, a2. These are just the powers of, or should I use x so that it will make more sense? x0, x1, x2. So these are the powers of x, right?
Why is one person bringing them?
No, like the person brings x, and based on that x, you just raise it to the power. So all these other values are dependent on x.
Okay. And this power you're raising it is based on the polynomial.
It's based on the polynomial, the degree of the polynomial. So this thing here is still the same thing as this.
Yeah.
I just like is it transpose they call it? I just transposed it, right?
Just you think the polynomial is x from 0
To 1 million, exactly. Yes. So that is also important because when it's important to cap the degree of your polynomial, right? You don't want, remember, like if we have 3 points, an infinite number of polynomials pass through 3 points, right? But there is only one polynomial of degree 2 that passes through these 3 points. So if your polynomial is actually a quadratic, but then you use powers up to degree 10, somebody that is cheating can pick one of those infinites here that pass through these 3 points and like basically try to use it and convince you, right? So that's why it's important that the degree of yeah, I can trust Linux. Okay, so let's wait for them to bring it out. Okay. Okay, so let's say it's necessary. It's necessary to address these things so that, as by the way, let's continue. Okay, so like this array is just a transposed version, right? It's just a transposed version of the powers of tau, right? So I'm going to take off this guy, and we are going to encrypt them. You know, to initialize these values, somebody has to actually start the ceremony, right? Somebody has to start the trusted setup ceremony. That person brings his own x, right? And then generates the powers of x, which is basically this array, right? After generating the powers of x, he encrypts all of them. He generates his powers of x in the clear. He knows his x, right? Then he encrypts it to get g of x to the 0, g to the x to the 1, g to the x to the 2, blah blah blah, right? So after the person has done this, it's now time for everybody to contribute, right? So if I want to contribute, what am I expected to do? Since these values now are points, right? So if you do the encryption and you send me this point, I don't know what your x is, right? I don't know what your x is, but I know you have given me the encrypted values of your x, but I don't know what your x is. I want to contribute. I want to add my own contribution, right? So what I do is I generate my own powers of x. Say my own x is a, right? I generate my a to the 0, a to the 1, a to the 2, blah blah blah, right? After I generate my own, I multiply my powers of a with the one you gave me. I don't know your own, but I know my own, right? And what is it going to give us? It's going to give us g to the x to the 0 to the a, right? G to the x to the 1 to the a to the 1, right? G to the x square to the a square, right? And this is going to give us g to the, it is a to the 0, right? G to the a x, like a to the 0, a to the 0, right? This will be g to the a to the 1, x to the 1. Yep. Okay, so next we have g, right, to the a square x squared, right? And like after the second person is done, this is what we're going to get. So we're going to get new encrypted values. This will be like the new set of values, right? And I don't know your x, right? And you don't know my a, right? But the both of us have been able to actually combine our different values to get a new set of values.
So other subsequent x's that other subsequent values that other people will bring will continue to build upon
that.
So it's going to continue to be g to the x to the ax to
Yeah.
So if 1 million people came together, so it will now be g
So
raised
the
to the power of 1 million
1
points
million,
on
exactly.
those different powers.
Exactly. Yeah. And if one person throws away the person's own x, there is no way to retrieve it. Yeah. But then like if everybody comes together, they can generate these values again, right? Because they'll just be bringing their values in the clay, right? And when they bring it together and multiply it together, they are going to get tau back. Right? So the final value for this, right, Okay, not this, right? Because this will be 1, right? G to the 0 is basically 1. Right? Oh, sorry, G to the 1. So the final value for this is our tau. Like after everybody has contributed. Right?
The last index.
Huh?
The last index.
The last index. Or the
Like
last
the
person.
Index, like maybe say A20, X20.
A, B, C, D, E,
A20.
Like that one
Is it A to the?
down.
Yeah.
Like G raised to the power of A20, X20. Let's say like the last person is, last index is 20.
The last person. Last index, are you talking about in this direction?
As it's going, yes.
No. What you're trying to say is like A to the or X to the 20.
Yes, yeah, like G raised to the power of A to the 20, X to the 20.
No, that now would be like the degree of the polynomial. That would be the degree of the polynomial, not the people's contribution. Because this will still be, let's say another person comes and the person brings B to the 1, B to the 0, B to the 2.
Still going to be that same G, that B, so that's the powers of
Yes.
that's
Oh, so
Yes.
like, someone brought the A, another person brought the X.
Yes, another person is bringing B. Another person can bring C. Another person can bring D. Just as many people as we have that participate in the trusted setup ceremony. Each of them is going to bring their own value for, let's call it X, their own X value.
So where does the index now come to? 0, 1, 2.
Like this one.
Yes, yes. Where is
That is the degree of the polynomial we're trying to commit to. You get? So why this is 2 is because this is the polynomial we're trying to commit to, right? And the degree is 2. So if we had plus, let's say D to the X to the 20, so that means this array is going to continue down until we get to G to the A to the 20, X to the 20, B to the 20. You get? Right? And these values are encrypted, right? Is it making sense?
Why are we not using the GA is power 0 instead of, why are we using the one of G is power
This one,
yeah.
A raised to the power 0 is what? 1. Anything raised to the power 0 is 1. So this will still be like G raised to the power 1.
So it means if we use that one, it means that for every component, whatever the component is, we're going to have a known value of tau.
If we use which one?
That's the 8 0 0 0. It means that you will know what tau is normally.
No.
No.
Like, basically, all these values combined together, that's what will give us our tau, right? And there's no how for you to know. This is just because we are actually outlining them. But when you're doing the actual multiplication, A to the power of 1 times X to the power of 1 will be equal to maybe C to the power of 1. And when we do times B to the power of 1, that is C to the power of 1 times B to the power of 1, will give us something new.
Yeah, I guess, but I'm just saying that if we use 8 to the power and the powers are 0, it means that it's almost know what tau is.
No, you can't. That is just the generator of the group, right? G to the 1 is the generator of the group, right? Is it making sense? Sure?
So,
So like
okay,
that,
in,
AX is down.
Yeah, this
Yeah.
is a tau.
So the
okay,
others,
A is not
others like
Like all these other values are just powers of, yes.
but in won't know tau since.
Yeah, you won't know tau since what you know is the x and the y coordinates. Is the points you know.
Right. So in KZG now,
Yeah.
who we're still not going to generate tau. We're still going to work like this.
Yes. Does it make sense?
Yeah, so for this now, when each person has their own bits of encryption to the initial process or whatever, it goes like sequentially. And gets the last person, right? How do you not generate it out? Because you still have like a set of points. So how do you not combine it to get that out?
So
Now
that's
is a scalar, right?
tau is a scalar, but we are not working with it in the scalar. We are working with it in the encrypted form
So it's still going to be like an array of
points. Yes, exactly. Huh? The powers of tau is the points. Yes, not tau itself, exactly.
But you mentioned that it would be like an array of points. So if 1 million people come together, it would be an array of 1 million points.
No. It will still be an array of, it depends on the degree of the polynomial.
Okay, yeah. So
What is encryption?
Yeah. So if the degree of the polynomial is 20, it's always going to be an array of 20 points. Even if 1 million people come together to generate it, it's always still going to be an array of 20 points. So this will be an array of 3 points.
When 1 million people came together, the G will be basically the power of the combination
Of those 1 million people, yes. Yeah, the degree of this polynomial is 2. You need degree plus 1 point. Or basically you can just think of it this way. Right? The constant here is a times x to the 0. Right? So we just want to have a way of evaluating the polynomial. Right? And we want to work with the encrypted values. Right?
So the process of encrypting is where we actually do G power of
Yes. I think that's Pedersen commitment. That's like, if you want to encrypt a value using like an elliptic curve, it's Pedersen commitment. So G to the power of that value, what you get is the commitment to that value of it. Pedersen. It's also a hash function. The Pedersen hash function. So when we say y equal to g to the x, we can think of y as a commitment to x, right? And this is like the Pedersen, y is the Pedersen commitment to x. Just like we had the Merkle root as the commitment to an array of values, right?
So after we get this commitment, tau,
Yeah.
G raised to power of tau is like the commitment to tau.
Yeah.
Then evaluating our polynomial at tau gives us commitment to our polynomial.
Yes. Evaluating our, like, not necessarily the, okay, evaluating our polynomial at tau, yes, gives us the commitment to the polynomial. But since we have the powers of tau, we can evaluate any polynomial at those powers of tau, right?
By powers of tau, we mean 0, 1, 2, 1.
This guy.
Okay.
So we can decide to use, like in this case, where was that example? Okay, so this A, B, C can be 2, 3, 4, right? It can be 1, 9, 8. It can be anything. And this one is a different polynomial, this is a different polynomial. But in as much as we have the powers of x, we can evaluate any of these polynomials at x. Right? Are we sure? Does it make sense?
Yeah.
To perform the operation, the power of ceremony based on each polynomial, not, or can you use the same power for different polynomials?
You can use the same tau for different polynomials.
Okay, I thought you always do that for, try a polynomial, perform the ceremony. I mean, the polynomial is significant, like, for a group or something.
Yeah.
I thought it was good for every time. I know it's possible for you to, like, use the same tau, right, but I thought it was, like, do it every time. You have, like, a new polynomial.
No, it's not compulsory. Even like Ethereum's trusted setup, Ethereum's powers of tau is public online. So if you want to perform, like if you want to actually commit to a polynomial and the degree of the polynomial is, let's say, the same or less than the one Ethereum did, if it's less than, you just take the parts you want, right? If it's the same, you take the entire powers of tau array and then use it. So it's public, like people use it for their different.
Like conduct your own ceremony.
Yeah, you don't need to always conduct unless you want to. But the idea is that people feel that that Ethereum's own is secure, right? Because of the amount of people that contributed. You get. So since tau is not known and we have the encrypted values, we can always use it, right? To commit to different polynomials. Hope it makes sense. Okay. So we've been talking about, but you know, like each group is going to have its own, right? Still the same powers of tau. You know, what do we say when we were talking about bilinear pairing? What is a bilinear map? Two elements from two different groups, so an element in a target group, right? So we have G1 and G2, and then we map it to GT, right? Right? And we can remember from yesterday that what was that equation in the encrypted? Okay, let's write it. The verifier, the KZG verifier check. What was it?
F of tau minus tau minus a cube of tau.
Right? And what did we say yesterday about the grouping? We said this can still be thought of as minus v, right? Times 1, right? It's equal to tau minus a times q of tau, right? And we said a bilinear map maps two elements from two different groups to an element in a target group, right? So we said this is basically in G1, right? And this is in G2, right? And yeah, this is G1, this is G2, right? Okay, you can actually do it anyway, right? But it's still like the both of them are still mapping to a target group, right? The both of them are still mapping to a target group. But I'm going to explain why I did it, why I switched it now. I'm going to explain that. But you can actually do it anyway. Okay. So like all of us are okay with the trusted setup ceremony, right? And we know how we can get our powers of tau, right? Good. So if we want to evaluate a polynomial and we have the powers of tau, how do we evaluate a polynomial? Dot products, right? So let's say our polynomial, still our usual polynomial, a square or a plus bx plus c square, cx square, right? And we have a, b, c, right? We're going to dot product it with our powers of tau, right? Which is g to the x to the 0, g to the x to the 1, g to the x to the 2. This is blah 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 on our own, right? So when we do this dot product, we are going to get g to the x to the 0 to the a, right? G to the x to the 1 to the b, g to the x to the 2 to the c, right? And what is that going to give us? Basically, g to the a, right? G to the bx, g to the cx squared, right? And when we add all of them together, we basically get g to the a plus bx plus cx squared, right? Is it making sense? So this is the process we go through when we want to actually evaluate a polynomial, right? Yeah, when we want to evaluate a polynomial at the powers of tau, that's when we do this, right? Do we agree?
So this is the same thing as just doing g raised to the power of the polynomial.
Yes. So this value, right, is still equal to g to the v.
Yes.
Which value?
This.
Oh, okay.
Do we agree?
It's still equals to what? How do you say that?
G to the v.
That's when you evaluate x. That's
Yeah.
A and whatever value.
Yeah. Okay, sorry. This, sorry, this value is the same thing as g to the to the to the tau. Sorry, g to the f of x. Yeah, this. Right?
How was that like? What are we doing?
Wait. Wakoli. Right. So yesterday we were wondering how are we evaluating a polynomial at tau without knowing tau, right? So that's what we're trying to demystify, right? How we can actually evaluate a polynomial at tau without knowing tau, right? We have seen how tau can be generated without anybody knowing tau. Have we?
Yes.
So we've seen how tau can be generated without anybody knowing tau
That is the combination
of those points.
those
Yeah.
values,
Yeah.
the x values from the random person.
Yes.
That's the tau.
Yeah, that's the tau. Then the array is the powers of tau. You get. So we have seen that, and now we just looked at how we can evaluate a polynomial with the powers of tau.
Our part of tau, it is as much as the
As the degree of the.
that means you can evaluate the just those sentiments.
Huh?
Because you can only evaluate the polynomial those sentiments. This one are just 3 points for this particular sentiment.
No, that means we can only evaluate the polynomial at x, not those 3 points. Because it's x that we are doing x to the 0, x to the 1, x to the 2. So is that x? Like, when we have f of x, right, to be equal to a plus bx plus cx squared. If we substitute a value here, f of 3, that means we are evaluating this polynomial at 3, right? We are not evaluating it at 3 to the 0, 3 to the 1, 3 to the 2. No. We are evaluating it at just 3. And in order to evaluate it at 3, we need to generate the powers of 3, right? In order to do this, we are now going to have like a, b, c, right? And then we are going to have the powers of 3. 3 to the 1, 3 to the 2. Right? And whatsoever thing we get is the evaluation of this polynomial f of x at 3. Yes. That's now when we do g to the 3 to the 0, right? G to the 3 to the 1, g to the 3 to the 2. The value, like after we evaluate it, we are going to get g to the f of x, right? Which is basically this. So that is what I was saying, that g to the f of x is equal to g to the a plus bx plus cx squared. Is it making sense? Sure.
It's somehow, here now, we are doing g raised power of f of x, which is g raised power of the polynomial, right? Is it that if let's say 10 persons are coming with x, it will now be g raised power of f of the x they are bringing to now evaluate the polynomial at that x?
Like those 10 persons, you're talking about the 10 people that contributed in the first set.
Yeah, we did the other one where we now did, like, we have an array that we have g raised power of, like, let's say the first person is coming with a. Okay, so with this array now, let's say the first person is coming with a, right? The person brings a raised power of. So the array will now be based on the degree of the polynomial, right?
Yes.
So, but what it's raising to is the combination of different values from different persons.
Yeah, all those values come together to form tau.
To form tau.
Yeah.
So
So you
now-
can,
okay.
you can also think of this as g to the tau to the 0, g to the tau to the 1, g to the tau to the 2.
Okay.
Because all these values are going to combine.
Okay. So let's go down to that new case.
Here.
Yeah. So now g raised power of tau, and here we're having g raised power of f of x, right? Like, what's the correlation between the both of them?
Like, this g here is the evaluation of the polynomial. This g to the tau, right? This is the powers of tau, right? This is the powers of tau.
G to the tau, like g to tau is power of
0,
Zero.
g to the tau to the 1,
One.
g to the tau to the 2, right?
Those
So
are
those
the
are the
powers
powers
of
of tau.
Yeah.
So when we want to evaluate a polynomial,
yeah.
we are going to do a dot product between the coefficients of that polynomial and the powers of tau.
Okay.
And when we do this dot product, we are going to now get, like when we reduce everything, we are going to get g to the polynomial.
Okay. G to the polynomial
Yes.
in tau.
Yes. When tau has been substituted,
Yes.
you
So
get
it's like the predicing commitment of that polynomial
yes
at tau.
at tau. Does it make sense?
Yeah. So what we are basically doing is that polynomial now will now substitute. We have got it tau. We just substitute tau to replace x in the polynomial.
Yes.
Okay.
So like since this is f of x, right?
Then
If
the f of tau.
it will be f of tau will now be equal to a plus b tau
Yeah.
plus c tau squared.
Yeah.
Why not change this on the
Okay.
because
No, it's because it's x I was using here.
no, it has changed it down technically.
Yeah.
Normal X.
But I hope it makes sense. Hope it makes sense.
Yeah.
Sure.
Wait. He said something that's the person commitment that start. I didn't get that part.
So, like, that's the evaluation of the polynomial at tau, right? And that's the commitment to the evaluation of the polynomial at tau. So, a Pedersen commitment, like I said initially, like let's say you have a value and you want to use the Pedersen commitment scheme to commit to it. You just raise it to the generator.
Yeah.
Let's say you want to commit to x.
Yeah.
You want to commit to x. So the commitment to x, which is y, is equal to the generator to the power of x.
Sure.
Yes.
This is
So
our
that's
Pedersen
what-
commitment.
Yeah, this is our Pedersen
Okay,
commitment.
that makes sense. So it's the English.
Yeah. So if you have f of x and you want to use Pedersen commitment to commit to
Just
it,
raise it.
yes, just g to the f of x. And if this is tau, and we know f of tau is our commitment, right? So when we have f of tau,
So this is just like the imputed value of
yes. Does it make sense?
yeah.
Okay. So now we've seen how we can evaluate a polynomial at a value we don't know, right? Because we don't know tau. A lot of people contributed to give us tau. We don't know tau, but then we can evaluate the polynomial at tau by doing a dot product of the coefficients of the polynomial and the powers of tau.
So technically, there's nothing keeping track of the people that are coming together to generate the powers of tau. Now, like, this. like you said, we don't know tau.
Yeah.
Now, if say 5 people comes together to generate that, then maybe like 7 additional persons now come, and like 12 persons in total. Is there nothing keeping track of like the number of persons that have come, what they've gotten and stuff like that, such that we know that okay, this is the amount of people that have come together to generate this value? Because if there is that kind of track, then that means that tau is known at that point, or there is a record for tau. But except they are not dropping their values.
They are not dropping their x values. Even if you know the total number of people that have come together to contribute, you don't know what the randomness they use.
Okay.
You don't know that x value that they added.
So it's not like they are coming together to now drop the randomness.
No. Does it make sense? Okay, so now let's go back to this equation. Right? Okay, so we know f of. Okay, so for now, let's think of it in terms of the polynomial, right? Right? We know the polynomial f of x, right? Or let's say on the prover side, the prover knows the polynomial f of x, right? Does it make sense? The prover knows the polynomial f of x,
Yes.
and that means he knows the coefficient of the polynomial, right? So if he wants to get f of tau, it's just to do a dot product of the coefficient of the polynomial and the powers of tau, right?
Yes.
Yeah.
That's everybody.
Yeah.
Okay. So the prover knows the polynomial f of x. The verifier doesn't. The prover just sends a commitment to the verifier, right? How does the prover get that commitment to the polynomial? Evaluate the polynomial at tau, right? And the prover does not know tau, but the prover has the powers of tau.
Just multiply.
What does verify mean?
If it
It
doesn't
doesn't mean it.
So the verifier wants to open the polynomial at a point. So we are starting like, let's go from the beginning.
You are turning back to working with the consent form now.
Eh?
You're turning back to working with consent form. Yes.
KZG is over univariate polynomial. Sorry,
I know
I
it's
did not.
Oh, KZG.
Yeah,
Why is it?
over univariate. Sorry, I did not mention it.
Why is what is it?
Like people have been thinking in terms of multilinear. Oh my god. Eh? Yes. With coefficient form, yes. Univariate coefficient form. But there is the multilinear KZG.
Can we do that one?
That's what people will be using for your. That's what you'll be using for your GKR actually. So we're just talking about KZG for now. We're still going to talk about multilinear KZG. So it's multilinear KZG people will be using to make your GKR succinct.
Sorry. Are we doing GKR again for this guy?
No, no, no.
The normal GKR we have done.
The normal GKR you have done, you will just make it succinct.
I mean,
Just like how you added Fiat Shemer, right? To make it non-interactive, right? So your normal GKR, you'll be able to generate a proof, right? But that proof will be big, right? So you want to reduce the size of the proof. So you use, yes, you now use the PCS, which is going to be multilinear KZG, in order to reduce the size of the proof. Sorry.
So, just like a quick reminder, like not like not like an action now. Just a quick reminder that you've not collected the law eating breakfast. Just a reminder. So, yeah, like I'm not saying like it should be, like actually be done now. Just reminder because
Can we push it to 12?
Sure. I'm just
Please. Please.
Yes.
Let's just push it to 12. Because by 12 we're going to take a break. Then you can go have breakfast, then come back and start implementation.
The implementation is it the KZG?
No.
You can continue our implementation.
Continue your GKR implementation.
Just kind of do this.
So you said that KZG is done over in Great.
Yeah.
That is standard.
The normal KZG, but they have multilinear KZG.
Is that okay? That multilinear KZG is just like, is that our like extending KZG to work for multilinear, or is this something that exists?
No, it's something that exists. It exists.
also, so the way is just easier to understand first.
Yeah. So the multilinear basically builds on the univariate. Yes.
If multilinear built on univariate,
I know where your head is going. But
you know, right?
yeah.
Because if multilinear builds on univariate and we are doing d plus 1 point, which means it's not always going to be this thing. It's not always going to be one. I don't know if you understand. It's not always going to be like one power, 1 degree of 1 or something. Multilinear, like power 1. So that means we need to look for a way to convert. And you know, the univariate we can actually convert to multilinear is in our sum check where we're converting univariate to multilinear. There, univariate is just still evaluation form, and it's the multilinear that we reduced, so it's still maintaining the same multilinear structure, so we can easily convert that univariate to multilinear easily. But in our GKR, the univariate is not multilinear, so we're now evaluating at d plus 1 point. So now if you want to perform KZG on multilinear and the but if you're performing it at multilinear, how are we going to do those powers of tau? Because multilinear is just one thing. How do you want to now do it to that? This is based on the degree. So because it's either we are using multilinear or we are using univariate and converting it somewhere somehow to multilinear.
It's not exactly the same protocol. Yeah. It's not exactly the same protocol, but understanding this one will help. Will help you. Okay, so the prover knows f of x, right? The prover knows f of x, right? Which is the polynomial. And he wants to commit to that polynomial. He has the powers of tau. Basically, everybody has the powers of tau, right? So he evaluates the polynomial at tau by doing a dot product, right, of the coefficients and the powers of tau to get f of tau. So prover knows the polynomial f of x, evaluates the polynomial at tau, right, to get f evaluated at tau. How does he do this? It's just the coefficients, the dot product with the powers of tau. Right? And that's for this first guy. You know, every group has its generator. Right? And here we're saying G1 and G2. G1 has its own generator. G2 has its own generator. G target has its own generator. Right? Okay, so when we are actually generating the powers of tau, we'll be generating it for two groups, G1 and G2. Right? Do we understand? I don't say anything complex, but do we understand? Like when we are generating the powers of tau, we are going to be generating it for two groups, G1 and G2. You can see this is G2 here, right? And this is tau. That means this tau has to be in G2, right? This tau and this A here has to be in G2. Sorry. This tau here and this A here, they have to be in G2, right? This one here has to be in G2.
So what are you?
Oh, sorry. This guy here has to be in G2. That one has to be in G2. This guy, tau and A, has to be in G2 so that we can subtract. You can subtract an element in G1 from an element in G2. You can only multiply an element in G1 and an element in G2 to get an element in GT with bilinear pairing. But when you want to subtract, you cannot subtract an element in G1 from an element in G2. They must be in the same group. Yes. Right? So these two guys are in G2. Right? So for G1, our commitment is in G1. Right? This value, which is the claimed evaluation of the polynomial, has to be in G1 too, so that we can subtract. Right? And the proof has to be in G1, right? So that we can do this multiplication between using bilinear pairing, right? So that we can do the multiplication between G2 and G1 to get an element in GT. Huh? The arrangement. Is it based on the G1 and G2? The G1, G2. Okay. So this is it. Right? This is a polynomial. This is a polynomial. Right? And in order to evaluate that polynomial at tau, we can do a dot product to the powers of tau in G, in what? In G1, right? So, huh? Yeah, it's bilinear pairing we use to do the multiplication. This
So
multiplication.
G1 and G2, what specifically?
G1 is a group, an elliptic curve group. G2 is another elliptic curve group. Is it making sense? So, this is a polynomial, right? And in order to evaluate that polynomial, we can do a dot product between the polynomial and the powers of tau, right? This too is a polynomial, right? In order to evaluate this polynomial, we can do a dot product of f of x and the powers of tau, right? One is just normal one, right? So we can just do the generator of G2 to the power of 1, right? And this guy here, this is tau minus A, and we don't know tau. How? And it's not a polynomial that we can say we can do a dot product, right?
Last question.
If anybody has the answer.
What was?
So I said f of tau, like f of x is a polynomial, right? So to evaluate it, we can do a dot product with the coefficients and the powers of tau. Q of x is a polynomial. To evaluate it, we can do a dot product of the coefficients and the powers of tau in G1. 1 is just a scalar, right? So we can do G2 to the power of 1, right? How about this guy, tau minus a?
Okay, we are sure that tau is greater than p. Greater than
Well,
equal to-
how can we do the subtraction if we don't know tau?
You take, now you take A to the,
And
you
you-
raise the generator to A, so they are both strong like points, and then you can operate on them.
Exactly.
Yeah.
So
Don't you respond?
yeah. So like that is what I was saying, that when we are doing the trusted setup, we're actually generating the powers of tau for two groups. Right? For G1 and for G2. Does it make sense? But now, for this guy, we don't need all the powers of tau. You know, like this is a polynomial. F of x is a polynomial. So we need all the powers of tau in order to bound it to a particular degree.
Yeah.
Q of x is a polynomial. So we need all the powers of tau in order to bound it to a particular degree.
Yeah.
Tau here is not a polynomial, right? So we don't need all the powers of tau because we're not trying to bound it to a particular degree. Right? We just need G2 to the power of tau. Right? And then we can do G2 to A. Right? And then we can subtract these two.
Yeah.
Make sense? Okay. So f of x is a polynomial, right? So you don't get eh? Wait.
You don't know that. How do we now do this to our account?
When
We
we're
just go to that part of that.
Keep one.
no, like I said, when we are doing the trusted setup ceremony, we're actually generating the powers of tau for two groups, right? For G1 and for G2. Yeah? You say?
I get that.
Yeah, because we need G1 and G2 in order to do the bilinear pairing. So when we're generating the powers of tau, we're actually generating the powers of tau for two groups, G1 and G2. Right. But now I'm trying to make us understand why it's not necessary to generate all the powers of tau for G2. Right. If you want, you can generate all the powers of tau for G2, but the particular one you will be working with is this one, the second one. Because the first one will always be G2 to the 1, right? The first one will always be G2 to the 1. The second one is what is going to be G2 to the tau. right?
Yes,
Sure.
Yeah.
So when we are generating the powers of tau for G2, we don't necessarily need to generate all the powers of tau, right? So we can just have the generator of G2, like when the person that instantiated the trusted setup instantiated it for G1, he did so with all the powers of tau, right? But for G2, he can just do G2 to the power of his own value of x, right? And then he sends it to the next person. The next person does this combination, right? And also does G2 that the previous person sent to the power of his own x, which is just like this one point in G2. I don't know if it's making sense.
That's it so far.
The G2 part. Sorry. Yeah?
Okay. So now for that G is for tau minus A, that would be G tau to 1, right?
Huh?
You will pick so yeah, that will be yeah. So we pick G to tau to 1 to represent our G to tau, right? That one we subtract for
Yeah.
the one with to
The one raised to the power of 1. That is this one. Okay, so let me go over it again. Well, we understand the whole trusted setup, right? Generating all the powers of tau for G1, right?
Yeah.
So let's talk about G2 now. You know, I said when we are doing our trusted setup, we are generating the powers of tau for two groups, G1 and G2. Right? So this same thing we are doing for G1, we're also going to do it for G2. You get? So normally you'll be expecting an array of values of points, two array of points, one for G1, one for G2. Right?
But G2 is just one.
Yeah, it's just one, but I'm trying to, like, let's first just get the picture that it can still be an array of points. Right? Yeah. So it can still, the same thing we did for G1. Just think about it that we do the same thing for G2. Right? The same way we generated the powers of tau for G1, we still generate the powers of tau for G2. The same way, the same time we are generating for G1, at that same time we are generating for G2.
So can you scroll down the way without that G1?
This one.
No, not here. Okay, here, yes, yes. So this side is G1, this side is G2. This side is G2, this side is. So are we generating for the both sides at the same time? Because like here now we have F into tau minus V as G1, multiplying 1 as G2. Then this other side we have tau minus A as G2, and we have 0 of tau as G1. So the G1 we are talking about is this G1, and the G2 we are talking about is the other G2 that is tau minus A, or is it for everything we are generating at once?
The same G1 we use here is the same G1 here, right?
Yeah?
This G1 here is the same G1 here, right? It's the same group. It's an elliptic curve group. Right? The thing is that this operation, we are doing this operation in the group.
And the group has a generator, which is a G.
Yes, the group has a generator, which is a
That
DG.
means the generator of this place is the same with the generator of
of this other one.
Okay,
Yeah.
and the generator G2 is same with generator on this other one.
Yes,
So that means this one and this one will be in the same group, and this one and this one will be in the same
in the
group.
same group, exactly.
And a group has two generators.
A group.
Yes.
A group can have two generators, but the two generators may not give all the elements of the group. You know, that's where we now talk about like subgroup.
So yeah, basically, these G1 and G2 are subgroups.
No. It's the same group. Wait, which G1 and G2?
G1.
No, this G1 and this G1 is the same group.
Theory.
Wait,
Okay.
this G1 and this G1 is the same
No, I'm
group.
not like G1 and G2.
Different groups.
Different groups
Yes.
on the same.
No, not on the same elliptic curve.
So we have two elliptic curves.
Two elliptic curves.
Oh, interesting.
Alright. So now
It's clear.
now we have our G1 and G2, right?
Yeah.
So that means the G1 is the same in both sides, the G2 is the same both sides.
Yeah.
Okay. So you said when we are generating, when we are creating our cluster setup, we generate it for two groups, that's G1 and G2, right?
Yes. So it's just like this. Here will be for G1. This will be G1 to the power of G1 to the power of G1 to the power of, right? Then for G2, it will be the generator of G2
With this same stuff.
to these same values.
Okay.
So that will give us two different arrays,
Yeah.
right? One for all the powers of tau in G1
Yeah.
and one for all the powers of tau in G2.
Okay. Okay, so now you are now
Makes
saying,
sense, right?
yes. Now you are now saying if we want to now scroll down, sorry, to where you have this. Okay. So now you are now saying that we don't have to like get all the powers of tau, like all the tau produced here
For the G2.
for the only for the G2.
Yes, only for the G2. Because for G1, we need to do the G1, f of x is a polynomial.
Yes.
And in order to evaluate that polynomial, we need to do a dot product of the powers of tau and the coefficients.
Yeah.
Q of x is also a polynomial. In order to do that polynomial evaluation, we need to do a dot product between the powers of tau and the coefficients of Q of x. But, okay, 1 here is just a scalar.
Yeah.
So we can just do G2 to the power of 1 to encrypt 1, right? Which is basically this first element,
Yeah.
right?
Yeah.
And then for this other guy, this is tau minus a. Tau is not a polynomial, right? So since tau is not a polynomial, we need to encrypt tau to get G2 to the tau, right? And we also need to encrypt a to get G2 to the a, right? We can get G2 to the a because we know a. A is the point the verifier wants to open at, right? So we can do G2 to the a. But we don't know tau. How can we now get tau? Basically, coming back to this trusted setup, right? G2 to the tau to the 1 is still G2 to the tau. So we just pick this guy in G2. So we are not using all the elements of this G2 array. The only elements we are basically using is this one at index 1.
At index 1 can give you back tau.
Yes.
Others will raise it
To the power. Yes, to different power. Yes, and the first one will be 1.
Yeah.
If you want, you can pick your G2 to the 1 here, but you can as well still do it by yourself, right? Because you know the generator of G2.
Yeah, yes.
So at this point, now know that
No, we don't know tau still.
You get
if
representation
we
for
are
like
picking a reference, you may not give us the result of that.
That's G2 to the tau, which is a point. But we don't know tau, which is a scalar.
So my question is that now, when we are doing our trusted set ceremony, we are considering 2 elliptic curves,
So elliptic curves, yes.
right?
Yes.
So now, what is the relationship between the 2 elliptic curves? Number 1,
That is the bilinear pairing.
the bilinear pairing enables us to do that.
To do multiplication between those two groups.
So the second, the generator of the second elliptic curve group, how do we, okay, now, the second elliptic curve, what is the polynomial there? Because we need to know the polynomial.
It will have its own
It will
polynomial.
have its own polynomial.
Just like the G1 too has its own
The
polynomial.
G1 polynomial is set to the G2 polynomial, because from the polynomial, that is when we now get the generator which is moving about. Then we get the generator to the power of tau, the generator of tau.
Yeah. So there are 2 different elliptic curve
Yes.
groups. They have their polynomial that defines them, and they also have their
So
generator.
now, why is tau in the other side the same thing? Tau in G1 is same. Is tau in G1 the same as tau in G2?
No.
No,
Yes.
they are different.
They are different because the generators are different.
No, the generators are obviously different. So
Yeah. So since the generators are different, the tau
we also
the tau is the same tau, right, that we are
Same tau.
using. Yes, but the
How come we are
point.
using the same tau? Since we have different, we have 2 elliptic curves.
Huh?
How come we are using the same tau since we are dealing with 2 different things? The only thing we can do is to pair them using bilinear pairing.
Well, the idea is indices. Indices works, right? Indices works.
Okay.
You get it?
So if indices work, if we have the same things, for example, now if I have
So
3 raised to power 5 multiplied by 5 raised to power 3, I can't do anything with that.
that is what I was saying. Bilinear pairing is what? Think about bilinear pairing as a black box that handles the multiplication. If you want to understand how bilinear pairing works, the more maths manual.
Yeah, I really
You
think
get it.
about bilinear pairing.
Yeah.
It's just we did something on the called bilinear math.
Yeah, it's basically you can think of it as a
So
bilinear
yeah,
map.
like 2 linear transformations, bringing them together to the one. That is G1. You have a map G1 to G2 that gives you G2.
Yeah.
So that is what bilinear pairing does. Or maybe later shall we look at it. I don't really understand how we have the same term in different groups, in different generators, groups of generators.
It doesn't matter, right? The main thing is tau we are working with, the encrypted value of tau, right? So you want us to change this tau?
No. Maybe what comes to the best alternative that is in my mind now is just that let's assume tau is 5. We can have 5 in first elliptic, we can have 5
In the
so tau
second.
does not-
Yes.
Tau
So
does not really
so it doesn't matter. What I was trying when I said it's not the same this thing, it's not the same point, right? So G to the tau in G1 will give us X and Y. That X and Y may be 5 and 3. The same G to the tau in G2 will give us its own X and Y. That X and Y may be 27 and 9. You get. But the thing now is that when we do the bilinear map of the 2 of them to the target group, they are going to give us the same value in the target group. Yes, exactly.
I guess.
So, that G2,
Yeah.
is it from G2 raised to power 8, power minus 8,
So
that we go to, is it from G2 to power minus 8,
yes.
that we go to G2 to power minus G2?
Right. This guy.
Yeah.
Yes. Right. So this tau minus a, right? And in order to get tau in G2, that was what we came to pick from here, right?
Now you use it as minus E. It was before you use it as E. If you use it as E, and it was
Dividing.
and you were subtracting before, it was to be divided.
Yes.
Yeah. So that was the difference.
So you can still take it as the inverse, right? And then when you multiply it, it's going to be an addition, tau minus a. Right? Hope it makes sense.
This power vector is there a
Huh?
yeah, mathematical representation
For the powers of tau. Like the entire powers or just
like
I'm not sure of that. But does this make sense up to this point? Sure. So basically we can see, okay, so now do we agree that you can actually evaluate a polynomial at a point you don't know? Eh? Nobody wants to agree.
Yes. But the G2 has, you said we don't need to evaluate it over the entire power of now.
Yeah, but do you understand like that we can just pick the second element in
The power of power.
in G2 array?
Yeah.
We can just pick the second element. Since we can just pick the second element, instead of doing all the powers of tau in G2, why don't we just encrypt tau and just keep working with that? Just that single value.
What do you call G raised to our power.
Yes. Or G raised to the power X, right? Let's say the guy, when he started it, he just started with G2 to the X, right? And then when the next person comes, for that G2 array, instead of doing the entire powers of tau for G2, he just does G2 to the X. Yeah, like it's a combination of everything that will give us tau, right? So that's like G2 to the X, right? When the next person comes, he just does to the A, right? When the next person comes, he does to the B. So eventually we're just going to get G2 to the XAB, where XAB is equal to tau. Right? So no need for us to like all the powers for G2, but we need to get all the powers for G1. So
So what was happening with X? So that means we're going to like substitute a value for X.
yeah, that is the initial, the person that instantiated the trusted
Substitute
setup,
value for X. Okay, that's the initial person. X represents the first
the
person.
first person. So if it's only one person that did the trusted setup, then the person can know tau, right? Because it was only the person's contribution that generated tau. So the person can know tau, right? And if everybody come together, they can just multiply their randomness and get style if everybody collude, right? But if only one person is honest and throws away the person's around honest, then even if every other person multiplies their own, they won't be able to get backed out because of that person's own that is not there, right? I don't know if it's making sense.
What is brute force?
Brute force.
What is before that final value?
That final one. Funny enough, you can't. Funny enough, you can't.
It's mathematically impossible.
Brute forcing for that one is basically like brute forcing to find tau. So even if every other person comes together except one person, it's as if you don't still know anything. Yeah, they are random.
That's what I'm saying. Like,
So if you want to brute force, then let everybody, like, there's no need for everybody to come together, right? Because even if they come together, the value they are going to get is not going to help. So it's better you just start from the beginning to start brute forcing instead of you to disturb yourself with gathering everybody together. I don't know if it's making sense. To get the already. Yeah, no, you don't want to say it.
This one looks almost like impossible to force. That one you can still maybe force it.
I want to say it's almost impossible to
Yeah.
force.
Unlikely that-
But in this one, like in that one we can have a threshold, right? But in this one there's no threshold.
I think it's easier to force if maybe everybody is available except one person.
because
Because now you've gotten every other person's stuff. You just want one person. So
One
you're just
person.
forcing combinations that
of that value,
that
is
value
what you have.
that. But if
So
it's
if you multiply those two, like everybody have come together, right? And they got a single value, right? And that single value, you're now trying to multiply. Okay, let's say
you don't even know where the I
Exactly.
get
Start with them from the beginning.
so if the entire group,
let's building.
So you have used all
You
the
don't know
things
if it's
So you have
after the
their
first
own,
person
you know,
that
the
person's
journey
own came in, or whether it came at the last.
so even if you know where, it's commutative, right? Like even if you know where, it's commutative.
That means it doesn't matter where.
It doesn't matter where.
Exactly.
So and because it doesn't matter where, wait, let me just give an illustration. So let's say we are working with numbers from 1 to 50. We are working mod 50, right? And then we are working mod 50, and then we have 10 people that came together to contribute. Each of those 10 people picked the values from 1 to 50. When we multiply all those values, we are going to get one number in 1 to 50, right? So if we have one number in 1 to 50, we're not trying to get that last person's own. That means in order to brute force, we need to multiply like everybody's own. Let's say, okay, let me give like a valid example. Let's say we have one, we are working with the set 1 to 50, right?
0 to 49.
Okay. Anyhow, like, you get the point. So we are working with the set 1 to 50, and then we have 10 people that actually came together to bring their randomness. Right? Let's say the first person did 2, 3, blah 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 up to 10. Right? We can just say everybody brought 2, but they did not know, right? So that would be 2 to the 9. What is 2 to the 9? 512, right? 512. So 512 mod 5 mod 50. That should be 12. Is it 12? Okay, so that's 12, right? For those 9 people, right? So that last person, we are trying to find out what are we going to multiply with this 12 to get tau. And tau is a number, right?
In a modular field.
In this modular in 1 to 50.
Yeah.
Tau is a number in 1 to 50, right? And you're now looking for what number are you going to multiply with 12 to get tau in 1 to 50. So you start going through all the numbers from 1 to 50. So what is the use of doing that extra multiplication when you can just brute force tau?
First, okay, 2 for 150, yeah.
So you're even doing more work by brute forcing and still doing the multiplication. So why not just throw away the multiplication and know that you're doing brute force? Yeah, it makes it more easy. But go and do it with 256. Yes, with numbers.
That makes everything less, more easier. Because it's like what we were talking about, like if we stop looking at cryptography and all of that now, you know those things have characters, they have A, B, C, D.
Those are numbers.
Or we are talking about password, whereby we have A, B, C.
Password, when you hash it, it's still a number.
This one we are
You don't even need to, like whether we're hashing it or not. It's like, if I want to hack you, I don't need to know your password if I can brute force.
Yes.
I'll just brute force from 1 to infinity.
Yes.
And at one point, I'm going to get your password.
Yes. So this one, are they hashing it or just putting numbers?
It's strictly now, whether they are hashing it or it's strictly numbers, everything boils down to numbers.
By 32 is still within.
Like, whether you're hashing it or you're not, everything boils down to numbers. So if you hash it, you're going to get a, say a number with 32 bits, right? But if you want, you can just brute force from 0 to 2 to the 32. Then you're basically removing that work of hashing. You don't need to do hashing again. If you want to do hashing, you're just stressing, you're killing your computer, like doing work that you shouldn't do.
So this is unlikely to happen.
Yes,
So
it's
that
not.
it's impossible.
It's virtually impossible, but it can happen.
It's unlikely.
highly
Yes,
Maybe
it's unlikely
conditions
to
can
happen.
cause it for it to happen.
Let's say with quantum computers, but that one is.
Just like
Eh? Passwords are numbers. In as much as you're hashing it. In as much as you're hashing it. Right? Even whether you hash it or not, you have to represent the password in binary. Right? Computer only understands binary. And in as much as you're representing that number in binary, you're actually, or in as much as you're representing that password in binary, you can actually convert that binary to a number. So it's just the same information but different ways to represent it. Everybody's password. Yes, and char. Exactly. So everybody just go and work on. Just go and work on how to just go and work on an efficient brute forcing algorithm and hack everybody's wallet. Okay, so does it make sense up to this point? Are we sure? So we understand how to get the commitment, right? which is the evaluation of the polynomial f of x at tau. How do we get that? By doing a dot product between the coefficients of the polynomial and the powers of tau, right? For v,
So that's how to get the community.
yes. So for v,
And the reason for the powers of tau is Ti.
ci,
Yeah, T is like I.
okay, like see that's tau, right?
Yeah, tau, sorry. Tau is like I.
Tau to the I, okay.
Can you just circle the one that is the commitment?
This is it.
F of t, that's the commitment.
F of tau. Yeah, and it's in G1.
It's in G1.
Yeah, it's in the G1 group, elliptic curve group.
Okay, yeah.
Yeah. And then V is in G1 too.
Yeah.
Right. And 1 is in G2. Tau minus A. I'm sure all of us
This
understand.
equation is the verifier's equation.
Yeah, this is what the verifier checks. And the verifier uses bilinear pairing to do this multiplication. This multiplication. Does it make sense?
Sorry.
Eh?
Based on this verifier, can we just see what the prover is doing again so that we can, it will help us appreciate this thing that this verifier is doing? Because I'm sure that the way what the prover is doing, the way the prover is setting it up, it helps the verifier work. Because if the prover is not like doing something right in terms of, like you said, when we are creating our setup, right? The prover is the one creating setup.
Trusted setup?
Yes.
No.
Okay, but trusted setup is created using all these powers of tau and the rest.
Yeah.
Okay. So that means that trusted setup creates like a structure that both the prover and the verifier will use.
Yes.
Okay, that means it's related.
But sorry, I think it should be the other way around. It is the verifier that should say what he wants. Then the prover goes and does it and comes back. So if we say this is the kind of verification we want to do, it's up to the prover to now follow steps and make sure that this verification passes for the support.
Like, this verification should always pass.
Yeah, that's what I'm saying. Like, it is the verifier that will say how he wants it to be done. So what I'm saying is, if we understand this verification, it is easier to come up with something that will pass this verification.
You don't even like, if the prover is honest, he will always come up
No,
with
I'm not
something.
talking about whether prover is wrong. I'm saying like, for us to understand
Yeah.
this thing, if we understand how verification is done, then it is easier to say, okay, this is how we need to write the prover.
So I think
Okay.
what he's saying in essence,
Maybe an example.
what
Right?
he's trying to say in essence is it like the verifier that chooses, because what is common between the verifier and the prover is the trusted setup.
Yeah.
That's what's common.
That is generating the
Yes,
tau.
that's what's common between the verifier and the prover. And once that is shared, the only thing the verifier is providing is the A,
Yes.
where he wants the prover to open to the
Polynomial.
but the trusted setup is shared among both of them.
Yeah.
So I think what he's saying is it the verifier that means the trusted setup to use?
No.
Like, because he's saying that the verifier is the one that tells the prover what to do.
Yeah, like telling the prover what to do, is it like the point to evaluate the polynomial?
Is that the
No, I'm just saying in general, it is the verifier that knows what he wants. It is not the prover to do it and show a proof that he has done what the verifier
Or the
wants.
verifier
That was
wants?
what I'm saying.
Okay.
So if that stands, so how does the verifier tell the prover what he wants? Because the only communication between the verifier and the prover is, okay, we have the same trusted setup and I want to open this polynomial at A. So the only thing the verifier is giving the prover is A, and they share trusted setup.
But the prover has to commit.
A.
Okay, let's just do like an example, right? We did one yesterday, but we'll do one again today, and maybe look at a dishonest prover, and then if a prover knows style, right?
Did you guys see that?
Oh my God. But I just want to be sure that everything we did today made sense.
We've done the trust.
Yeah, we've done the trust etc.
But we did finish.
No, like after breakfast, so bit to play. No, that'll be tomorrow. That'll be tomorrow. Okay, so I want to be sure that everything we did today made sense.
I don't understand what's the conclusion of the binomial what are we doing?
We are equating, yes. We are multiplying these two, and then we check if the value we get is equal to where we multiply this other two.
So, since we don't know how do we get the multiply? Do we still
The prover, no, like the commitment, the prover will evaluate the polynomial at tau, which is the commitment, by doing that dot product of the coefficients and the powers of tau you get to get the commitment. Hey, come on, can we do this exam? Okay, so the prover commits to the polynomial first. That's the first thing, right? The trusted setup is done, blah blah blah, and we have our powers of tau array. Then the prover comes. I want to commit to a polynomial. It comes to the verifier. I want to commit to this polynomial, so that you can tell me to evaluate this polynomial at any other time in the future, right? So he commits to the polynomial by evaluating that polynomial at tau. How does he evaluate the polynomial at tau? By doing a dot product between the coefficients of the polynomial and the powers of tau. He's going to get a point in G1.
That first polynomial, I commit to, is it known to the verifier?
No, it's known to only the prover. That is a hiding property of commitment scheme. So it's known to only the prover, but the prover evaluates that polynomial at tau and sends it to the verifier, which is the commitment. So since the verifier now has the commitment, the verifier wants to open that polynomial that has been committed to at a particular point. He sends A, which is the point he wants to evaluate the polynomial at, to the prover. The prover evaluates the polynomial at A and generates a proof. He evaluates the polynomial at A to get V, right? And also generates a proof, Q of tau. So he sends V and Q of tau to the verifier. You know, the verifier already has F of tau, which is the commitment. So now the prover is sending so So the verifier already has F of tau, which is the commitment, right? Then the prover sent, the verifier also has A, right? Because that is the point he wants to evaluate the polynomial at. Then the prover sends V, which is the result of evaluating the polynomial at A, right? And the proof, right? To the verifier. So with these values, the verifier can do this. He can do this, right? He knows A, and basically he also has G of tau, right? So he can do G of minus A, right, to evaluate this part, and then the prover has sent the proof. No, the evaluation of f of x at A. That's B. Is it making sense?
Let's come again with the
Initially, the prover commits to the polynomial, which is by evaluating the polynomial at tau.
Sorry, sir. The A, is it the evaluation of the, like, f of x? The A is
The point we want to evaluate at. Then V, yes, I will give V. Sorry, Raima.
Yeah, I was asking if that's the beginning
Of the protocol. So, to begin the protocol, we need to generate the powers of tau. Yeah, we can use any random, like any other powers of tau ceremony or any other trusted setup ceremony that has been done.
But what if there are two groups that have like different genes? This is like if I use a different, let's say the different then I want to do that different, I want to do
Oh no.
that's pretty simple.
Yeah, there are specific groups that actually have this bilinear pairing relationship. It's not all groups. So that's why, like, when we talk of pairing friendly calls, if you've heard of pairing friendly calls before, so it's just talking about like calls that are pairing friendly. It has this bilinear relationship, like BLS 12381 is one of those. So you most likely be using BLS 12381 when you want to implement. Yeah, you can't use BL254. I don't think BL254 is pairing friendly.
I read somewhere that I think school use BM254 while zero is BLS. So that's I think
Like most of them, like Ethereum, I think most times they use a combination of both to achieve different goals, right? Like for the signature aggregation, I think Ethereum uses BLS 12381 for signature aggregation. That is attestation. Like when the validators want to attest to a block, I think the aggregation is, I think it's BLS 12381 they use. Huh? Yes, yes.
So, tau minus it. Wait, so I also know my
Huh?
tau minus it when I know the tau. So that's something like 5 minutes two.
Yeah,
Value the tau. So you're turning it to generator.
yeah.
And when you turn both of them to generators, then you multiply them.
It will be those of subtraction. You get the tau minus it.
You get, for example, what you look up to now, you probably get G into tau minus A or minus tau A. Like when you combine the powers,
This will be G to the tau plus minus A.
so G to the tau minus A.
So which is G to the tau
Minus A.
minus A, which is
When
this.
you're doing a generator like this, you still don't know the power. And what we need is that power manager. How do you get the power manager itself from this generation?
You don't know it, but it's happening.
So when it happens, how do you now put this back into this equation? Because you will not put the G to power manager back into the equation.
Yeah, that's why this is a point. Look at it here. It's a point in G2. So by linear pairing, you're doing a multiplication of elliptical points. So it's a point.
So you need to add this to the power manager.
Yeah, you can just use it in the bilinear pairing.
So there's no way to get for G2. So this one can go.
Okay, so I think we're going to call it a day today. Let's say, yeah. So tomorrow maybe we are going to now do like an example. Yeah. So any other question? Okay.